Okay, to start with, we are looking at linear algebra. Is an important part of algebra. There are many forms of algebra. 3701 is linear algebra, but there's also abstract algebra. There are many forms of algebra in mathematics in general. Okay, as part of what the students need to know in this module, they must be in a position to understand subspaces. So, for example, a question that is so basic in this module is the notion of what we call a subspace. A subspace begins by, as it says, a subset of a finite dimensional vector space. So the vector spaces we study here are finite dimensional over a field such that the vector space can be written as a sum of two finite dimensional subspaces. So you need to prove, therefore, that V is the direct sum. If and only if the dimension of the finite dimensional vector space V is actually the sum of the dimensions of the subspaces. Okay, a very important result for 8 marks. How do we go about proving this? So, right, we get started with the proof until we begin to understand what is happening here. So now to prove a statement like this in mathematics, where you say this equals that if and only if this is the case, how do we prove that? So obviously, if and only if in mathematics um, two is double-headed, right? Is double-headed that way. So there are a couple of things then that we actually can consider here. Right, we note that. Right, so we note that. Right, we need to note that first and foremost, the dimension of the vector space V, right, is the dimension of, okay, because V is U plus W. So dimension of V is U plus W. Right. Now, so what kind of a dimension is this? So um the U plus W, you can see it as, you can think of this as a union. What is the dimension of the union? In mathematics, that is dimension of U plus the dimension of W minus the dimension of the intersection, like this. Okay, this is what we get. This is what we get. If it therefore happens, right, if V is the direct sum, it is called direct sum. So V now is the direct sum of the two subspaces. Okay, what does it mean to speak of the direct sum? If V is the direct sum, it actually means that U intersection W is is trivial. Okay, so if you have V equals the direct sum of U and W, then it means that U intersection W is trivial. Okay, so if it is trivial, what does it mean? So what is the dimension of the zero set, the zero vector space? What is the dimension of the zero vector space? This is called the zero vector space because it contains only zero. The trivial vector space is a very important trivial vector space in mathematics. So you find therefore here the dimension of the intersection, right? So you find dimension of the intersection, okay? Right, discussing a very important result. Right, so you find that this therefore is a dimension of the intersection. So we find the dimension of U intersection W. Right, what's the dimension of U intersection W? It is the dimension of 0. The dimension of 0 is 0. Why? Right, so we note therefore the dimension of the trivial vector space is 0. Why is it 0? Well, it is 0 because um, the dimension is nothing other than the number of the linearly independent vectors in a subspace. So there are 0 um, linearly independent vectors here, and therefore this is 0. Dimension is 0. Okay, I'm gonna look at that in detail at some point, but just note that dimension of the 0 vector space is 0, and therefore, okay, the dimension of V. What's the dimension of V? Right. So the dimension of V now, if you found that the dimension of the intersection is 0, so it means the dimension of V is just the dimension of U plus the dimension of W. Right. So it means the dimension of V here is the dimension of U plus the dimension of W. Right. Okay. So what have we got? Did we do? So now we say we're supposed to prove that this V is the direct sum. Okay, this plus in a circle is called direct sum if and only if the dimension of V is the sum of the dimensions of U and W. Right, so you need to start from one side because it's if and only if. So we started with, actually, this is where the proof starts. Here we're just citing what the actual formula states for for the dimension of a vector space V. So now we started with U plus W. Then if V is U plus W direct sum, okay, because by definition of direct sum, if V is a direct sum of two subspaces, then it means in mathematics that the intersection of the two subspaces is trivial. We say it's a trivial intersection because it contains 0. And so this is just a property of the direct sum. I'm sure it means the dimension of 0 is of the 0 subspace is 0. And therefore the dimension, if this one is 0 in this formula, it means the dimension of V is U plus W. Okay, conversely. So now we have proven that if we have this, we have dimension of V is U plus W dimension there. Now we actually consider the converse. So we start from the conclusion and now achieve or try to derive the premise. So beginning from the conclusion, we say conversely. Now we look at the converse. Conversely, we start from the conclusion. Conversely, if the dimension of, now we start by writing this. So we start by saying the dimension of V, if dimension of V is the dimension of U plus the dimension of W. Then, okay, so if this is the case, okay, so you start by writing this. Okay, so we start this. If this is true, the dimension of V is the dimension of U plus W. How do we achieve the direct sum from that? We reason, right? Then in mathematics, if this is direct sum, then it means that the dimension of U intersection W It means dimension of U intersection W is actually 0. In mathematics, if this is true, it means the dimension of the intersection of these two subspaces is 0. So that, right? So that if this dimension is 0, what does it mean? If the dimension is 0, well, it means therefore U intersection W is trivial. Okay, well, if the dimension is 0, it means U intersection W is consists of 0 because the dimension is 0. So it means the intersection does not have a non-zero vector. Thus, thus, if the intersection does not have, or the intersection consists of 0, thus it means that V is equal to is the direct sum. If this is consists of 0, that means that V is actually U plus W direct sum. Um, so we achieve this. We achieve that. And then now, once we achieve that, which is exactly that part. So we started here and then we have exactly that part. Um, and we note that obviously this is true since in both directions we have already this here. It's part of the assumption from the beginning. Since already we already have that. We already have that V is U plus W. Okay. So because V equals U plus W is given. So from the intersection, we can write the direct sum. This one, the trivial intersection, together with the sum of U plus W equal to V given, it actually means a direct sum. Okay, this is just a proof there. But that must be known for exam for about 8 marks in this module. The next question. Okay, as part of what must be learned, the idea of a T-cyclic basis, right? A T-cyclic basis, the characteristic polynomial, a TW121 map, TW is onto, right? The module for the first time, the exam is going to be set by a different person, but this person is not a difficult person. Quite, they have a very good. The professor who has been setting these exams for the past. He worked at UNICEF all his life. Has just recently retired. I think the last exam he said was January this year. Okay, so um, we expect another professor to deal with this. Okay, let's look at the first question. Right, so if you look at the fact that I've broken these questions down into pieces that we can be able to digest. Right, so will that now be a map? It is a linear operator from M33. Now, M3 cross 3 is the vector. This is the vector space of 3 by 3 matrices with complex entries to the vector space of 3 by 3 matrices with complex entries be the linear operator over C defined by Tx equals Ax. So this linear operator is defined as the product of the matrix A times an arbitrary vector in M 3 cross 3 of C. Let W be the T-cyclic subspace. So let W be the T-cyclic subspace. Right, we shall understand what that means and the T-cyclic subspace because we need to find the basis of it. Right, of 3 by or of the 3 by 3 matrices generated by A. Find the T-cyclic basis for W. W is generated by A. Let's find it. How do we find that? So obviously we find that by means of repeated multiplication. So to find the T-cyclics, because now we expect this question, the professor normally uses the approach of the former lecturer, and so we really can expect these kinds of questions to pop tomorrow. Okay, on T-cyclic basis. Right. So the matrix A is actually given like that. So you always write the matrix A because we use it um, to generate the basis. A basis is a set that is generated by repeated multiplication. So A is there, 1, 0, 0, 0, and then you have um, 1, 0, 0, 0, 1, 1. Okay, you have these. The next thing is we obtain another matrix, the TA matrix. Right, it is a T-cyclic subspace for W. But look, W is generated by A. W is a T-cyclic subspace generated by A. Here, how does the matrix A generate the subspace? So we obtain the T of A using always use the definition of the linear operator. So we're going to use TA. According to this definition, what is TA? If we replace every x by A, so it becomes TA is equal to what? Is equal to A times A, which is what? Which is A squared. And therefore, we have what is A squared? Is A 0, 0, 0, 0, 0, 0, 1, 1. So we have this 0, 0, 0, 1, 0, 0, 0, 1, 1. Okay, so we continue. We multiply this with that, 0, this with that, this with that. In other words, multiplying this row by this column, 0 by 0 is 0, 0 by 1 is 0, 0 by that. So you have this with that, it's going to be 0. This with that, it's 0. Okay, then you have this one with that one, 0. This row by this column, 0. This row by this column is 0. This row by this column, that's going to be 0 by 0, then it's going to be 1 here, and this is going to be 0, so it's 1 here. And then this row by this column is going to be 0, 0, then 1. This row by this column is going to 0, 0, 1, like this. That's CA. Next, we continue. Okay, we found already TA. Now we studied the pattern here. We studied the repetition of at what point do we need to stop. So we're going to look at the next thing. The next thing is we found TA, then we find T squared now. We're going to, because we took A and then we obtained TA. But now we need to obtain the next thing. So we obtain T of this one, T of TA. Right, obtaining T of TA to obtain a second, we just continue like that. T of TA is the same as repeated application of T twice is T squared of A. What is T squared of A? Right. So in other words, we use this formula. What is T squared of A here? Right, so T squared of A is really the same as, so given T, which is this one, you replace every X by TA here. So according to that definition, if wherever there is X, you put TA, so that's going to be TA. Wherever there is X, you put TA, so that's going to be TA. And then what did you get TA to be? We got TA to be what? A squared. So TTA is A cubed. So here you get A cubed. So this one becomes A cubed. Okay. Um, right. We're just learning how to generate a T-cyclic basis. Okay, because it's a concept that's very important in this module. Right. So after having found the cube, we cube the matrix A. Right. So if you cube the matrix A, what is the cube of the matrix A? Right, you can look at it in two ways. To get the cube of the matrix A, you get the square of the matrix A times the matrix A. What is the square of the matrix A? It's this one. So for the square, you can get this one. So you can look at it as having A squared, then you multiply by A, like this. Okay, so what is A squared? You copy this A squared, is that one, which is 0, 0, 0, that. And then what is A? It's that one. 0, 0, 0, and then you have 1, 0, 0, and then 0, 1, 1. Okay, you multiply this matrix here, all right? So you multiply this with that, so you get 0. This with that, 0. This with that, 0. This with that. This with that, 0. This with that, 0. This with that, 0. This with that, 0. This with that is 1. Okay. This row by that column is 1. This row by that column, which I'll only have this one matching. The other 1 by 0, 1 by 0, plus 1 by 1, 1. So T of TA is this one, and this is exactly the same as what? This actually very important observation. So it means T of TA is actually the same as TA. Right. Now, this is an important step here, because if it happens, therefore, that we get this, right, we get this. So what do we do with this? So we take this and we use this. Right. So the T-cyclic basis, the T-cyclic basis for W is, what is the T-cyclic basis for W? Right, the T-cyclic basis for W generated by, so generated by A, the matrix A. We started by the matrix A, but TA then also came into the picture. Then we tried to get T squared, but T squared is the same as TA. So in other words, we stop at TA. So the T-cyclic basis consists of these two elements. Since it is linearly, right, it is linearly independent. Always, all bases in in linear algebra have this linear independence property, linearly independence, linearly independent. And since it is linearly independent, and the t squared we got actually became equal to what? T squared became equal to T of A. Okay. Anyway, we're just finding a T-cyclic basis. How to define a T-cyclic basis? We start with the element A, and then we have the repeated multiplication of the linear operator on the matrix A. And now we generate more elements, and we put the elements into what we call the basis. They form the basis. Right, next question on T-cyclic basis. We need to be able to find the characteristic polynomial. So the question is, how do you find characteristic polynomial? Obviously, linear algebra 2. In linear algebra 2, we're able to get the characteristic polynomial. But now, how do we find the characteristic polynomial? So we use the fact that, for instance, since we at the point where this whole thing terminates, right, we use the fact that t squared became equal to ta. So this became equal to the previous. T squared became equal to just ta. All right. The characteristic, right? The characteristic polynomial, the characteristic polynomial of t subscript w is okay. We're looking for the characteristic polynomial of t subscript w. Right. What is it the same as? It is the same as. So we call it c subscript tw. All right. It's evaluated at t. And what is this? Right. So what you do is you take minus one, always minus one, but always minus one. Then you square it with the highest power that equaled the previous.
Hello.
Yes, please.
Where did this come from?
Okay, where did this come from? It came from the previous results. It came from this point because at this point we found t squared, but t squared became equal to t of a because t squared, what did t squared become? T squared became this one, the zeros and ones at the bottom, and ta was had the zeros and ones at the bottom. So we realized therefore that in our attempt to find ta, t squared became equal to just t squared is this, and it became just equal to ta. Okay, with that, we're able to see that since, so we always use that, the fact that now t squared is actually became equal to ta. So the characteristic polynomial of tw now, we use this formula because that is what is the terminating step of the t-cyclic basis. Right, so we take this and we use it to find the characteristic polynomial. There are many ways to do this, but yeah. Okay, so after having used this, then we say minus 1 to the power. All right, so it was t squared that became equal to the previous. So we put a square on the minus 1 like that. And therefore, inside this, you put this is the same as t squared equals that, but these can be translated to be the same as t squared of a, like this, minus t of a. So, which means here we're going to put t squared minus t. Right, so it's exactly what we get. So this becomes the characteristic polynomial. Right, and this characteristic polynomial can be written out because if you square minus 1, it is plus 1. Then you multiply out, you multiply through, giving us t squared minus what? Minus t. Okay, so this is the characteristic polynomial. How do we get the characteristic polynomial? We simply um, take minus 1 and we raise it to the power that terminated. Okay, and the power that terminated, that was equal to the previous, became the square on the minus one. Then what do you put here? You put the polynomial that the t's suggest. So this is saying t squared equals t, but it must be equal to 0 here. So it's t squared minus t. And then now if you square minus 1, it's plus 1. And therefore the characteristic polynomial of t subscript tw of t is t squared minus t. Now the next question. Okay, this characteristic polynomial, you can also find it by actually um, quickly finding the characteristic polynomial of these using the eigenvalues method from uh, second year linear algebra. Okay, in 2.3 now, you must be able to explain whether t is 1 to 1. Okay, so in other words, now we have found the polynomial, is it 1 to 1 or not? So we have found, obviously, that the CTW of t is actually t squared minus t, and we found that this is a quadratic polynomial. Is it 1 to 1 or not? Right, to explain the 1 to 1ness, we realize that it is not 1 to 1. Okay, it's a function this. You can use many ways to explain if it is a 1 to 1 function or not. Right, so it is not. Why is it not? It is not since 0. is a root, is a root of TTW. So explain whether TW is one to one or not. It is not because 0 is a root. So if ever 0 is a root of this, how is 0 a root of this? Okay, obviously on the side, one can see how you find the root. So the root is CTW is 0. Okay, okay, then you're finding the root, which is then t squared minus t equals 0. You have t into t minus 1 equals 0. This is t0 or t is 1. Okay, so these are the two roots. But no, since 0 is a root, so if 0 is a root, it means that the polynomial is not one to one. Okay, so that is one easy method we use. Okay, so this is just some brainstorming on the side, but this is the answer to the question. Is T one to one? It is not because 0 is a root of the characteristic polynomial of W. Okay, 2.4, explain whether it is onto. Okay, as how to start of this, you remember that obviously C2W of T is actually T squared minus T. Explain whether it's onto. Is this onto or not? Okay, a couple of ways obviously to look at this. This is just a polynomial, but the reason is that it is not. No. Right. Why is it not onto? Since PW is not one to one. Okay, this is a wonderful relationship between one to one operator and the onto operator. See, we're saying no since the TW is not one to one. Okay, so we have that. So we're saying no since TW is not one to one. Okay, what are we saying here? For the linear operators, if it's one to one, this is not just for any functions. A one to one operate linear operator is an onto linear operator. So if it is one to one, then it's onto. But obviously, this is true for linear operators, but not just for functions in general. Now we continue. Right, we still have the same question. For each eigenvalue of TW, find a corresponding eigenvector expresses a linear combination of the T-cyclic spaces for W for a total of 8 marks. Okay, so this one is an eigenvalue, eigenvector situation. All right, so we note that from 2.1, right, from question 2.1, what did we learn here? Right, from question 2.1, we learned that t squared was equal to TA, which means that t, we learned that t squared of A was equal to TA, and this is actually from the 2.1 question. So this means that t of t minus A, okay, so we write like this, t minus I, so you have this. So you have this. So this is exactly TA. Okay, so just note that one. Okay, let me just clean this up a little bit. Right, so we have therefore that, okay, For each eigenvalue, find the corresponding eigenvector. So we find the eigenvectors from the quadratic polynomial. This is how we do it. So we make it equal to 0 by transposing everything from the right. If you transpose this one, it becomes c squared minus c, which is this. Right, so you have this one, which is t minus I, like this, t of a, and this is equal to 0. And this is the same as, okay, so thus this is t minus I of a, t minus I of a, which we're taking this one, this part, the t minus I part, but we are applying it to a, not t of a. Right, so what does this give us? It gives us ta minus um, minus I of a, but I is the identity map, so it fixes the matrix. So I of a, like this. So this one is an eigenvector, is an eigenvector. Okay, you just learn how to find eigenvectors here. So the eigenvectors, we found them in terms of the linear operator. Okay, so this one becomes an eigenvector. Um, is an eigenvector of what? Is an eigenvector of TW associated associated with lambda equals 0. Okay, this one becomes um an eigenvector of TW associated with lambda equal to 0 because the vector is coming from this equation here. So the eigenvector, how do you find the eigenvector? So you start here. Right, from second year, we learned that the eigenvector is matrix times x is the same as the eigenvalue times x. Okay, this in mathematics became a very powerful equation that gave birth to the eigenvalues in mathematics. Why was it so interesting this? Because all these things we're doing are based on this equation. A matrix times a vector is equal to a number times the same vector. And therefore, mathematicians became interested in finding this number that behaves, that also sort of operates as a matrix. Because how can a matrix times a one vector equal to a number times the same vector? Has the matrix is the matrix equal to the number? It raised so many questions. But we're then saying here, thus this t minus I, this thing here, is an eigenvector of TW associated with lambda equal to 0. Associated with lambda equal to 0. Why lambda equal to 0? Well, what it is saying is that you have t of these is 0. Okay, we have this. And t of a is an eigenvector. Is an eigenvector of TW associated with, okay, now we're speaking of and t of a. What is t of a? And where do we see t of a? Right, so obviously t of a is an eigenvector. Now t of a is here. For we actually get that or T of A can be seen here as well. This is equal to this. So T of A is here. Is an eigenvector of TW associated with lambda equals that. Lambda equals 1. Okay, lambda equals 1 comes from here because this is like a T minus the thing that sits next to the I is lambda because if you have a matrix like this, you can write it like that. So we always transpose this because AX equals lambda X is always AX minus lambda X. So you can factor out the X, factor out the X. So you have A minus lambda. The lambda equals 1. Okay, okay, so what have we got now? Do we set for each eigenvalue? Find the corresponding eigenvector. So we therefore set here, thus this one, t minus that is an eigenvector. So the t minus this, which is a t minus I, or t minus I, is an eigenvector of TW associated with lambda equals 0. Why associated with lambda equals 0? Associated with this, right. So in other words, the t minus that is an eigenvector associated with lambda equals 0. So the eigenvector is what is within the t operator. But also for TA, we say the same. We say TA is the eigenvector of TW associated with this TA is associated with this one here. A little bit interesting because now we are looking at TA is an eigenvector of TW associated with lambda equals 1. Where is lambda equals 1? If this is like T minus that, and you find the lambda that is sitting next to that. So the lambda equals is not minus 1, but it is 1. Because to find the lambda, you take this to the other side. You take this to the other side, so you take this to the other side of 0, meaning lambda is 1. Okay, so just you note that one there. All right, so we get this. Um, so we continue. Next question. Okay, as part of what we learn, we must learn the test for diagonalizability. So we must know if a T is diagonalizable or not. Right, so to know if T is diagonalizable or not, a couple of things that remain extremely important. What are those things that remain very important? What is the test for diagonalizability at this point? Right, so let's look at the test for diagonalizability at this point. Right, so to test for diagonalizability, to know if T is diagonalizable or not. Okay, so expect a question like that as well tomorrow on testing for diagonalizability and how we do this test. So to do this test, I have made space available. Next slide. Sure, did I not? Okay, right. So to show that T is diagonalizable, we consider the map, this one. We consider the map, this one. How do we test for diagonal? We let beta denote the standard basis for R3. Okay, we let beta denote the standard basis for R3. Then what do we say? P of sub beta. Okay, because now this is from R3 to R3. So what is the standard basis for R3? Right, we learn about the standard basis. Let's know the standard basis of R3. Then beta, you can write out here. Then beta contains the standard vectors. The standard vectors are the 0, 1, 0 vector. So you contain these vectors. These are basically unit vectors in the three-dimensional space, like this. Right, so in the end, you have this three-dimensional space, this one here, that is unit vectors here. So the unit vector here is called the I vector, which is 1, 0, 0. This one is the J vector. J vector along the y-axis has 1 in the middle, because these other triples themselves contain the x, y, z vectors. Right, so the z vector is 0, 0, 1, because x, y, z is the order of the vectors, vector components. Now, um, what do we say here? Then, if we look at T sub b, okay, for example, so you get this here. So this one is A, B, C. So which means you have A, B, C. So it means that for at the top, you're going to have 2, 1, 0. Then you have the second one. A is 1, B has the coefficient 2, and C has the coefficient 0. The bottom one has the coefficient A is coefficient 1, B is coefficient 1, C is coefficient 1. Okay, so that. Then we can find the determinant of this. So the determinant of lambda I minus the subscript beta. Okay, so this is how it is for diagonalizability. So you take the linear operator, you convert the function to a matrix. By looking at the fact that this one, the A is coefficient 2, the B is coefficient 1, the C is coefficient 0, because there's no C in the first component. Second component has those coefficients: A coefficient 1, B coefficient 2, C coefficient 0. The last one is 1, 1, 1. So then we have lambda I minus T sub B. Right, we have this. Okay, what is T? So we say lambda I minus this matrix here. Lambda I, what is I? I is the 1, 0, 0, 0, 1, 0, 0, 0, 1. So what is lambda I? You have minus this. So it's lambda minus 2. You have 1. And then you have lambda minus 2. And then you have lambda minus 1. Right. And then we find the determinant of this.
Hello?
Yes, please, Saman.
How did you get this?
Okay, wait, is that coming from? It's coming from exactly this map here. Okay. A couple of ways to imagine that. Let me do it in green. Right. So you can do it here and see how it actually arises. So it's T is a representation of the beta natural basis. So how do we do that? So it means that you take every vector and you write it as a linear combination of these vectors here. Right. So um, that would mean that, for example, what is the image of the under T100? T of, you take the vectors from here, that's why it's T subscript beta. So this
I
one is,
think I understand.
yeah, I'm sure you understand. So that if you have this now, you have um, A, B, C, because the vectors have A, B, C components. So if you put here, it means A is 1. Okay, A is 1 and B and C is 0. So if you put A1, what is 2 times 1? It's going to be 2. A is 1, B is 0. A is 1. One way to see that is to realize the fool that the first vector is going to be the 2 and 1 vector, and then also the 0, 1, 0. 0, 1, 0 is the A, B, C. Because the vectors are A, B, C here. So it means here, what is 1 is the middle one, A, B, C. So B is 1. You put B1 here everywhere, and A and C is 0. B is 1. B is 1, so that's going to be 2. B is 1, that's going to be 1. So it's 1 to 1. So you can make this 1 to 1. Okay, there are many ways to look at it. Right. So in other words, these vectors themselves, where are they coming from? They're coming from the basis beta. That is why we said let this one be not the standard basis. What is the standard basis? Is the basis that contains zeros and ones. So the last one, for instance, in this one would be the 001 vector. 001 vector means that you have A, B, C. The C is 1 and everything else is 0. So if the C is 1, C is 1. So this is going to be 0, 0. The C is 1. C is 1. So you have 001. Okay. Um, but like I said, alternatively, you can look at it as follows. You can look at this as another way to look at it is to look at these T, A, B, C. You can write these as a column vectors. You can write it as 2A plus B. And then this second one is, so you can write this as a column vector like this. And then now, in other words, so you can take even this one, the points like the 100 is a vector. It can be written as 100. You can write it as a column vector. Okay, from the notion of a column vector, then you can be able to factorize this. Because if this is that, in mathematics, you can write it like, okay, I'm going to write on top of this. Right, so you're going to write as, for example, just to clean the, remove this red line here. Okay, so this vector, you can write it like as follows. Right, so you can write this one is, so you can cut this out here, and then now you can write this A, B, C. So you can factorize this out. After you factorize this out, you look at the coefficients of A. The coefficient of A is 2. The coefficient of B is 1. The coefficient of C is 0. And then now you come here. The coefficient of A is 1. The coefficient of B is 2. The coefficient of C is 0. So you can factorize as well. And this only happens if it means that you are considering the zeros and ones. So this happens if the basis, underlying basis is the standard basis, right, with zeros and ones. And then you have 1, 1, 1. So this is the same in mathematics because if you do the row by column multiplication to multiply these two matrices, you get that back, which is exactly that. Okay, what have we got now? We're doing the test for diagonalizability, and then we're getting this. If you multiply this out, you have lambda minus 2 into this one, 0. Um, so we get this. All right, after this, then you can um, oh, you can call this one. Ah, okay. You can expand. My point is you can expand this one along your row of choice. So you can have -1 here, -2, 0, that. So you can decide to expand uh, along that. Okay, if you expand along this column here, you will have only this one because now this one is positive, negative, positive, positive, negative, positive, negative, positive, negative. This one negative, positive, negative, positive. So look, then you have this one is which is positive. So you have lambda -1. And then you have this, which is the minor of this entry here. Called the minor. This is called the minor. Right. And then you get that. But now if you multiply out, so it becomes lambda -1. This one into this one here, which is lambda -2. Okay, we have this. So it's lambda -1 squared. Right, this one here is going to be lambda minus what? It's going to be lambda -3. I'm sorry for congesting everything here. You get that. What is this? Okay, let's move to the next slide. Hence, what we have is that the determinant of, we always start with lambda I minus t subscript beta. Is lambda that squared or lambda -3? Um, so that, so that now you have I minus t subscript lambda um, with respect to the standard basis beta with the zeros and ones like we may explained above. So this one, what is this the same as? Right. What is this the same as? Okay. It is exactly the same as 1 is to 1, 0, 0, 0, 1, 0, 0, 0, 1. That is the identity matrix minus this. So this is actually coming from the lambda I minus p sub b representation we wrote earlier for the test as a test for diagonalizability. Now, what is T sub b? Okay, T sub b is the matrix we got, which was 2, 1, 0, 1, 2, 0, 1, 1, 1. Okay, so you subtract this. If you subtract this, you have 1 minus 2. What is 1 minus 2? Is minus 1. The rest is minus 1. 0. Okay, this is minus. This is 1 minus 2 is minus 1. 0. Minus 1. Minus 0. Um, okay. This is exactly minus. Right here. Minus into 1, 1, 0, 1, 1, 0, 1, 1, 0. Okay. And it follows that. Right. And it follows that the rank. Okay, right. Which is the number of non-zero rows. It's called the rank. Right. I have another student who is stressed up by the honors project I was still because now I was completing it. Yes, Semaketa. Yes, I understand you stressed up. You stressed up. Now I'm just concluding a discussion here. I will actually just get back to you in a couple of minutes. So that we submit the honors project. I know that obviously I delayed and I was trying to push the project. Right. So yeah, just give me a couple of minutes. I will send it to you so that we get it submitted. Okay. Yeah, even that guy is waiting. So right, just give me a couple of minutes. I'll just be getting back to you now so that I can send you guys the projects so you can submit quickly. Okay. All right. My apologies. Okay, okay, thanks, Maketa. Yeah, please tell that guy as well because I know he's a bit stressed out because it's closing midnight and I was trying to push. Yeah, okay. All right, thanks, Maketa. I'll keep you posted now. Like, okay, thanks. Goodbye. Right, so you have the rank, which is that. So, right, it follows therefore that the rank of this, right, so you have that this rank, the rank of this, which is the rank of this. So now, in other words, we have taken lambda to be equal to 1. Okay, we have taken lambda to be equal to 1. And then if you take lambda to be equal to 1 here, you put it here, it gives us this. It gives us the negative matrix then. If one, there's a minus in front. Okay, normally we don't speak about negative matrices, but there's a minus in front. That's what one is saying here. Right, so it follows therefore that the rank of this minus p sub b, which is this minus that, the rank of this is 1. Okay, the rank is 1. How do you find the rank? Okay, I'll come to that quickly. Okay, so you reduce this to reduce the Reuteran form, and then you find that the rank is 1. Okay, so that the dimension, you find the dimension of the eigenspace. Eigenspace associated with lambda equals 1 because we did this for lambda equals 1. So the eigenspace consists of the dimension of the eigenspace becomes 2, which is equal to multiplicity multiplicity of lambda equals 1. Okay. Right. You need to note that the rank is 1. And if the rank is 1, so it means that you have one row that is non-zero. And the rest will become 0 by row reduction. Right. Because by row reduction, you'll have that this one is going to be minus 1, 1, 0. This one you can do row 2 minus row 1, row 3 minus row 1. Okay, if you say this minus this, because they're the same, it's going to be 0. This minus that. So obviously by row reduction, you have the rank 1. But the dimension then is 2. the dimension of the eigenspace. So it means the eigenvectors, this dimension of the eigenspace means the eigenvectors, you count them, there are two of them there. So the multiplicity then is 1. Multiplicity is 1. The multiplicity of lambda equals 1. So the multiplicity is um, the power in the characteristic polynomial. So it is 2. If this is 2, and the vector, the dimension of the eigenspace is also 2, right, which is the multiplicity of lambda equals 1. Therefore, T is diagonalizable. Okay, look at what we've done for diagonalizability. We just looked at the power 2, and then we investigated this one because it could make the matrix defective and not diagonalizable. So the only case, if this now is of characteristic 2, if it's of multiplicity is 2, it we need two vectors for this. We need two eigenvectors for this. But we have two eigenvectors from the fact that now if the rank is 1, the rank is 1, that means the dimension of the eigenspace is 2. Why? Because now um, the dimension of this is a 3 by 3 matrix. Um, 2 plus 1, 2 plus 1, 2 plus 1 is 3. So this is diagonalizable because of this. All right. I've been on air for like about 1 hour. I know that there's a lot we need to discuss, but I think that I'll have to take a short break. Right. There's this student now who's also stressing up something because of the project due time. I tried to push the project, but this guy just gave me in the 11th hour, and now I need to just give them so that they just submit.
Can we end the recording?
Okay, thank you. Let me just end the recording. Um.